All right, here we are looking at what are called improper integrals, and there are two types, and we're going to just take on type 1. Type 1 is where you have area under a curve, and the curve is going out to infinity, and this can happen on either the right hand or the left hand side, but I'll just show it here going out to the right. And the question is, if this goes hugging this asymptotically, and you're starting at some point A and you're going out to infinity, what happens with this area? Now this one, it looks like it's crashing down pretty quickly down to the line. Maybe that gives you a hint that yes, some of these do have finite areas, even though they go infinitely in its right-hand direction. But some of them do not have a finite area. They have infinite area, and we'll learn a rule about that, I think maybe at the end. But right now, we're just going to go through an example here of what to do. And the way we approach this, where we're going out to an infinite distance, is we set it up as a limit. And we say the limit, as we can use any variable, but t is customary often. We're going to let t go to infinity as we evaluate this integral from 4 out to t, and then we still have the function in terms of x. And I'm going to rewrite this as 1/2 minus 1/2 x dx. So when we evaluate this integral, our upper limit here is t, and then we just let t go to infinity. Okay, well, what is this integral? You could do this with simple substitution, but hopefully we're expert enough that we see that this integral can be found as minus 2 then e to the minus 1/2 x. If I take the derivative of this, the minus 1/2 comes out, cancels and all that. And so I still got the limit. Half the battle doing these is just remembering how to write the notation without forgetting this. And then what am I taking the limit of? I'm taking this as it's evaluated then from 4 out to t. Okay, so when I plug in t here, and I am going to run out of space, but I'll try to write it small. It's going to be the limit still as t goes to infinity. And then the first part of this is going to be when I plug in t there, it's going to be minus, and then I'm going to put 2 up on top and put e to the 1/2 t down below, e to the 1/2 t down below. And then I'm going to take away from that the same thing, subtract from that, and then it's going to be minus 2. I'll sneak that up above, and then down below is e to the, well, when I plug in 4, that's going to be 4 over 2, and that is 2. And I put it down below so the negative sign is taken care of, and there it is. Okay, well, what is that limit? All right, if I evaluate this limit now, here, as t gets larger and larger and larger, this denominator gets huge, and it's 2 over something that's huge, and it's negative. So this becomes negative 0 minus, and inside that is minus 2, and this is just e to the second power. So that's just e to the second. Well, that is the limit. So minus a minus gives us an answer. I guess I can put it here. It's just going to be positive 2 over e squared. Okay, so that is what the area is under that curve. So that means that it does converge, we say. And we're doing the limit to see if it's finite, and it's saying if it's finite, then it converges. In a moment, we might be able to say whether it converges first, and then use that to find the improper integral. Okay, so here's another one. This one, we can set it up. We have a little bit more space to write. We have the limit as t goes to, in this case, infinity, and it's going to be of this integral from 1 to t. And this variable match is always so that when we set it up, we're letting the boundary, that limit, go farther and farther out to the right in this case. Well, the limit here, I'm going to do a little bit of rewriting right off the bat, and you'll see why. But I'm going to write that as 1/2, and then I'm going to say 2x plus 2 all over x squared plus 2x, and then dx. And the reason for that is just that I'm looking down the road to when I actually do the integration here. Notice that if I'm hoping that this is something I can do by parts or by substitution, and very conveniently, it's a bit contrived, but the derivative of this denominator is exactly that in the numerator. And I found that by just saying, well, what is the relationship here? Well, normally if you've got an x squared and an x, you can do it by substitution, but that extra x complicates it, but not in this particular case, because if I take the derivative, I get 2x plus 2, and that is obviously very similar to that. All I need to do is factor out the 1/2. So that's kind of maybe a little bit lucky, but there you go. All right, once I get this then, what is the actual integration here? Well, I can write this down below. It's going to be, in this case, the ln of x squared plus 2x. Okay, I should make that absolute value. And then remember, that's going from 1 to t, and I have that 1/2 that's going to come out front and going to come all the way out front. So it's going to be 1/2, and that limit is going to be as t approaches infinity. All right? So what is that? Well, that's going to be 1/2, and then as I look at this and I substitute in t, it's going to be the limit as t goes to infinity of t squared plus 2t, and then minus, when I plug in 1 plus the, sorry, that should say ln. That's, yeah, there, that's, I knew I left a little bit of space. See, half the battle is, remember, that's the ln, because I've got 1 over my u substitution. I did a substitution, u equals x squared plus 2x, and then du equals 2x plus 2, which is 1/2 then of du is equal to x plus 1. Anyway, that's the ln there. So this is the limit as x goes to infinity, and this is the ln of that minus the ln of 3. All right. Well, what is the limit as t goes to infinity of t squared plus 2t? Even though taking the log of a number going to infinity slows it down a bit, it still goes to infinity. And at this stage, you just stop, because once one part of it goes to infinity, it does not matter that this is finite. It does not matter that we're taking and cutting 1/2 of infinity. It's still infinity, so it diverges. All right, sorry to make a mess of that, but that is the way it works out sometime. Hopefully I won't make a mess of this one. We have another problem. This one's got e in it as well. This looks suspiciously like we're going to have to do this by parts, but I'm going to set it up as the limit, again, as t goes to infinity of this integral from 0 to t of x e to the minus 5x dx. Okay, well, this is parts, and that's my algebra part. This is my exponential part. So I'm going to do this first. So I've got u is equal to x, and du is equal to dx. If you can do this in your head, that's great, but this is one that maybe is a little bit tougher. dv then is equal to e to the minus 5x dx. And then v then is going to be equal to, let's see, minus 1/5 e to the minus 5x. So going down this way and going up that way keeps that all square. And so this then is equal to, well, the limit still as t goes to infinity. And now this will be x times, I'm going to put the x up in the numerator, so it'll be minus x over 5 e to the minus 5x. Remember, when we do integration by parts, then I've got this second integral. And again, I'm just going to write this as 0 to t, and that kind of reminds me at this stage I've got 0 to t right there, because that is completed. And then this becomes this integral here, so that's a minus right there. So this minus becomes a plus.